Hello, everyone. Today we'll be discussing the solution to problem one of the USACO February 2026 Silver Contest. So in this problem, you're simulating a game where you have a hand consisting of 8 cards and a queue of cards you can draw from, and each card takes a certain amount of Mu Elixir to play. Every second you generate one new Mu Elixir. Some of these cards are win conditions, and you have the requirement that if you have at least one win condition in your hand, then the next card you play must be a win condition. And the task is you need to answer queries of the form, what are the maximum number of win conditions you can play in T seconds? So let's walk through a sample test case to see how this process goes. So in this sample, we have 6 cards, and the first 3 cards are the ones that are in our hand. The next 3 cards are the ones in the draw queue. And we're told that card 1 and card 4 are the win conditions. And here you can see the Mu Elixir that each card is worth. From now on, I'll be referring to the cards by the amount of Mu Elixir they have. So initially at time 0, we have cards 2, 4, and 3 in our hand, and 5, 7, and 6 in the queue. And since we have a win condition in our hand, which is 2, we have to play it. So we wait 2 seconds until we have 2 Mu Elixir, and then we play that card. So at time 2, we have we play card 2. It goes to the back of our queue, and we replace it with the top of our queue, which is the 5. And then we can keep going doing this process. So the 5 is a win condition in our hand, so we must play it. So we wait 5 seconds, and at time 7, we play the 5. And again, it goes to the back of the queue and replaced by the 7 at the top of the queue. And let's say the next card, we don't have a win condition in our hand now. So we can pick any of the cards to play next. Let's say we pick the 3. Then 3 seconds later, at time 10, we can play the 3. It goes to the back of our queue and it's replaced by the next one and so on. And we can repeat this process. So the next, let's say next we pick the 4 and the 4 goes to the back. And now the 2, which is the card we played initially, comes back into our hand. And the goal is, given queries on the number of seconds I have, you want to print the answer of what is the maximum number of win conditions you can get in that amount of time. Okay, so now let's think about what the optimal strategy would be for someone playing this game. Since we're trying to maximize the number of win conditions we play within a given time limit, it makes sense to prioritize cards with less Mu Elixir, since it takes less time to generate the Mu Elixir in order to play them. So this leads us to the following greedy strategy, where there's 2 cases. If we don't currently have a win condition in our hand, then we'll just play the card with the minimum Mu Elixir. Otherwise, if we do, we choose the win condition in our hand with the minimum Mu Elixir. And it turns out this greedy strategy is optimal. And you can prove this by sort of seeing proving it's never optimal to wait to play a card with higher Mu Elixir, since all win conditions are worth the same and all non-win conditions are equally worthless. And however, directly simulating this would still be too slow, as T can be very large. And so we still need some observations in order to optimize this process. So one of the observations we can make from observing the sample and our own test cases is that it seems that the process should eventually cycle. Or in other words, we should eventually play the same set of cards over and over in the same order. So for example, if we look at where we ended off in the sample test case, at time 14, our first card we played, card 2, is back in the queue now. And the next card we're going to play is going to be that 2, right? Since it's the minimum card and it's our only win condition. And you can see if you look forward in the future one step, the next card that will come from the draw queue is the 5, which we will also play. So it seems like we're cycling back to the cards we played on the first 2 turns. And it turns out this is true. So the main key observation we need to make to solve this problem is that the first n minus h plus 1 cards we play are the only cards we play, and we play it in that order. We keep cycling. And the first n minus 1 plus h card, like n minus h plus 1 cards, that's just the number of cards we need until we get back to the first card, until the first card comes back into our hand. And to sort of understand why, let's think about what happens on that turn when the first card comes back into our hand. So let's say, what if we don't pick the first card this time? What if we pick a better card, right? So if there's a better card in our hand on this turn, the only place it could have come from is the draw queue, right? If it didn't come from the draw queue, then we would have picked it on the first turn. But if it came from the draw queue, then it would be the best card on that turn. So we would have picked it as soon as it came from the draw queue. So since we didn't pick it, that means the first card is still our best card. And this logic applies for the next turns and all future turns. So therefore, we can prove that like on turn two, we'll pick the same card as we did. Um, and we'll keep going in this cycle. So this gives us our solution idea. So what we can do is we can simulate the first n minus h plus 1 cards based on our strategy above. And to do this efficiently, we can use a priority queue to keep track of the current win condition with the minimum mu elixir and the current non-win condition with the minimum mu elixir. And after we simulate the first n minus h plus 1 cards, we can calculate the time it takes to go through this whole cycle once and the number of win conditions in this cycle. And also for these first n minus h plus 1 cards, we can store like the time we played this card and the number of win conditions up to that time. And this allows us to do the following for each query. So for each query t, essentially we can take the number of cycles that we can fit within that time t. So if we can take t mod the time it takes for one big cycle, and we can process that all at once. We can multiply the number of win conditions per cycle by the number of cycles we can fit in time t. And then for the remaining time, we can use like the times that each of the first n minus h1 plus 1 cards were played, and we can binary search on that list to determine the number of win conditions uh, up to that point and the number of win conditions we can play in the remaining time. And so adding these two up will give us our answer for each query. Okay, so now let's implement this solution. So here you have the Python code. Right now it just reads the input. The first thing we'll want to do is import our library since we need our priority queue. Then we can store the win conditions with a Boolean array since it's more convenient for us than a list. And now we want to essentially initialize our priority queues with the current cards in our hand. So if the card's a win condition, we put it in the priority queue with win conditions. Otherwise, we put it in the priority queue with non-win conditions. And then we can simulate the first n minus h plus 1 turns. So to do that, we're going to keep track of the time that we play each of the first n minus h plus 1 cards and the total number of conditions up to that point. And we'll go through the remaining cards in the draw queue. And essentially, if we have a win condition, then we'll essentially play the minimum win condition and we'll update our time and the win condition we played. Otherwise, we'll just play the non-win condition with the minimum mu elixir and add that to our time. And we can store that time and the number of win conditions so far in our arrays. And if we've reached the end of our array, we've played all of our cards, then we can break. Otherwise, we need to update. We need to add the new card from the draw queue to our current hand. So this just updates our priority queues with the new card. And so this has just simulated our process. And now we have stored the total time for the cycle, the total number of win conditions in our cycle in these two variables. And for each card in the cycle, we've stored the time it was played and the total number of win conditions up to that point. And this allows us to answer each of our queries. So to get each of our queries, first we'll read in the input, and essentially we'll take the query time mod the time it takes for the entire cycle. So this is the time it takes for the whole cycle. And this represents the number of cycles we can do within that time, the query time. And so we'll multiply the number of cycles we can do within the query time by the number of win conditions per cycle. And this is right now represents the remaining time, which is essentially the time modulo the time for a cycle. And we can binary search on this array of times for the first n minus h plus 1 cards to find the number of win conditions we can do in the remaining time we have. So this essentially binary searches for the time, first time, which is like less than the remaining time t. And we can just add, if this exists, we can add the number of win conditions we played up to that time to our answer. And we will just print the answer at the end. And now we can test our code on a simple test case. And you can see it gives the right answer, and the solution gets full credit on USACO. Thanks for watching. I hope you all learned something new from this video.